Here we go. Okay, so let me go ahead and share the iPad screen. And let's take a look at another example. So we're not going to work all the way through this one, but what I want to do is show you how it's similar to the last one. So the last one, just quickly going back there, we know that once you're already factored and set equal to 0, we can set each factor to 0. It only works when you have equals 0. That's the key. And if you don't have something factored, but you have it equal to 0, factoring is going to be a technique. Or if you don't have it equal to 0, get it equal to 0 and factor. So if you remember that as the big overarching principle, the next actual 3 are very, very similar. So the one I had picked up next for us was sine cubed of x. There's at least one interesting thing on Desmos about this. Minus sine of x equals 0. Now, just a quick note, you can't type, Desmos note, if you're trying to type sine cubed into Desmos, you have to do it sine x cubed. Sorry, you guys are hearing some sound from my little one there. Some music background here. I think it's gone now. So just be careful when you're typing this in to check it, that you're careful. Don't do anything with higher than the power 2 on Desmos. It doesn't know what to do. But before we get to Desmos, if we're thinking about factoring this, we can factor out sine. So that we have sine of x squared. Sorry, I should say that better. Sine squared of x, right? Because we're squaring sine. We're not squaring the x part. Just be careful there. And then we have minus 1. Now, is it possible that we could see some, or you could see some in your homework, where you have an x squared in the argument of your trig function? Sure, you could. We're not going to see as many of those, but it's possible. Right? Kind of a different solution technique there. But once we get here, really brackets or parentheses, but a lot of times when I get to this step, I'm just thinking set each factor to 0 because I factored, right? Which is not a problem. If you set each factor to 0 and go ahead and add that 1, you get sine squared equals 1. And where you have to be careful on this one is where you have a squared and you take a square root, you have to remember you're going to have a plus or minus. Now, I was noticing on one of the Desmos slides in our activity to come, they represented this as the absolute value of sine of x equals 1, which is true, but it's always easier for my brain to go ahead and write the plus or minus rather than think about that absolute value. I'll kind of show you where that is in a few minutes so you can see. But this is actually now giving me this guy and 2 more. So sine of x equals 1, sine of x equals negative 1. And I'm going to have to continue each of these to get the solution or solutions out of each one. Now keep in mind, you're going to have potentially more than one solution for each one. Okay, so this does not mean there are 3 specific solutions. It means there's now 3 kind of sub-equations that we may solve and look at between 0 to 2 pi. So once we get here, it's pretty similar to the last one, just looking at sine, but definitely go back and kind of finish this one and revisit it, similar to your homework. But let's go ahead and take a look at another one. We're going to work this one all the way through. And it is 9 secant squared x minus 9 secant of x equals 18. So let's take a look at what we could do. First thing that jumps out to me is I have an equation and I have squares in it, kind of like our case before. And what you want to do is think about, this is very similar to 9 squared minus 9y squared minus 9y equals 18. It's basically a quadratic equation with trig thrown in. So if we recognize it like that, we know what to do over here with these y's. We know we need to go ahead and subtract the 18 and then either factor or I'd probably factor out my 9 and then try to factor. I could run into some quadratic formula, which is not going to be a ton of fun if we have to do that for trig, but it's possible. And we know that because there's some trig values with square root of 3 over 2, you could see that. So let's take a look at going ahead and tuning in everything. So factor out the 9. Divide by 9, and you still have secant squared x minus secant x minus 2 equals 0. And I just like to do kind of a parallel thing over here. So if ever I get confused, I just think about factoring pairwise. Okay, so let's take a minute, see if it factors. Hopefully it does. You're going to see that a lot of things work out nicely in this one, in this particular section. So you can practice the trig component and not get caught up in messy decimals. So 2 and a 1, so like a minus 2 plus 1. Make sure that works. So it gives me negative 2 plus 1y. Looks good. So in this case, secant of x plus 1 times secant of x minus 2 equals 0. So when we set our first equation, or our first factor equal to 0, we get secant of x equals negative 1, and then secant of x equals 2. And we set our brains, my brain, y'all, does not think in terms of secant of x equals 2 and jumping to a solution. I need to think about cosine, right? So cosine of x equals 1/2, and cosine of x equals the reciprocal of negative 1. We still have negative 1. Kind of nice. And can we solve from here? Sure. And I think it's kind of nice to get the Desmos complement, because you could have, if the cosine is 1/2, the secant is 2, but the secant graph has those asymptotes. So the graphical solution looks a little different than the other ones. So we'll explore. So let's just rewrite those. We're just kind of picking those up from the bottom. And then let's think about unit circle on this guy. We want our x value to be negative 1, so it looks like we are at pi. Any others? Not really here. And then if we think about unit circle, we should be looking in quadrants 1 and 2. And then hopefully we remember, while looking at our unit circle, we can see that the angle we should be looking for is pi over 3 in the first quadrant, and negative pi over 3 in the fourth. But instead of negative pi over 3, we can go ahead and say 5 pi over 3. Okay, so let's take a look at checking these between 0 and 2 pi, and then we'll write our generals. Questions before I change this over to Desmos? Okay, so we kind of see this rolls a lot of our inverse trig, domain issues, coterminal angles, plus our algebraic skills all together in one. Very cumulative problems. So by the time we get ready for the optional format, which maybe I'll talk more about that at the end today, talk about kind of our pacing again, then you're going to be in good shape after we practice this section in particular. So let me stop that share. And then share, switch the screen over here. There we go. And my teacher Desmos pulled up, which I'll share with you guys in just a second. But go back to your original, and I'm just going to type in the 9 sequence. That's here. remember, the flip equation is going to give us the x values only when we look at those. And let's see. Faces are on the solution again, but there is pi over 3 drop. Then we have 5 pi over 3. And then let's see. We have a problem, right? And we need to reconcile what's going on here because two things could be going on. We could have overlooked something on our algebraic section or our by hand section should be perfect, not really algebraic, looking at combining algebra and trig. Or Desmos could be doing something that we didn't intend for it to do. Both are plausible. Because if you look at what we did by hand, we had 3 solutions, right? And we need to look back carefully and ask ourselves, well, why am I not seeing the pi, the x equals pi that I was seeing before? Okay, so let's make sure everything's typed in. Data entry errors are always case number 1. So you guys take a look at this, see if you see any errors. I think that looks good. And if we really wanted to, if we were worried about this window and not seeing that third one, I could type 2 pi again. It's actually showing you kind of the next one out. But what I'm focusing on here is we wrote down 3 by hand and I only see 2. All right, so anything anyone sees wrong with Desmos, you can drop it in the chat. I'm not seeing anything. So let's stop the share and let's go back and carefully analyze our by hand work. You know, a troubleshoot when these don't agree is almost harder than just solving the problem in the first place. Okay, so first thing I would investigate is which part this one came from. So the 2 solutions that we actually saw on our Desmos page came from the cosine x equals 1/2 part. We saw the pi over 3 and we saw the 5 pi over 3. Balance back, yep. Make sure I'm looking at the right thing there. So pi over 3, 5 pi over 3, we saw these things. And then this guy is the one that you didn't see. And if we take a look back at the original equation, we always want to make sure the x values that we find work. In other words, if you plug them back into the original, do they actually work? Right? And a lot of times when we're checking, we just kind of solve for x and then we look back and say, oh yeah. But if you remember from other situations, may apply here, may not, we'll investigate, but you could have extraneous solutions. Where I like to think about extraneous solutions is for logarithms. When you're looking at logarithmic equations, we often get extraneous solutions. Or when you are working with exponentials combined with quadratics, you can get some extraneous solutions. In other words, you get an x value, but it doesn't work when you try to plug it back in. Okay, so that's tricky, right? And that may be the case here, or we may have just made a mistake. So let's look back. If I want to check this guy, I'm trying to check whether x equals pi. Seems like I could plug it in. Okay, so if you think about plugging this in, let's just squeeze it in. Let me get rid of the stuff. I don't want to need this anymore. Think about your pi and plugging it in. 9 secant squared of pi minus 9 secant of pi. We want to see if that equals 18. It actually checks. And we're focusing on the left side. So let's work through it. And if it checks, then maybe we'll look at Desmos and say, hey, Desmos, what are you doing? So if we think about this, put it back in terms of cosine. This helps us understand our problem, potentially. Because when we're thinking about the cosine of pi, the cosine of pi is going to be -1. And -1, I don't really have any problems plugging that in. So let's do it. Now, what if we had gotten 0? 0 would have been a problem. We would have had division by 0. But that's not the case here. You just kind of have to be on your toes at every step, right? So I'm going to plug in. And I really need to be careful here because I'm doing cosine squared. And I know cosine of pi is -1. But cosine squared of pi is going to be 1 because I'm taking that -1 and squaring it. Okay, so that's one thing that gets tricky. And we're still checking to see if that equals 18. Okay, so let's evaluate. We get 9, and then we're gonna have +9. Looks to give me 18. Looks to check. So it looks like it does this again. And let's actually switch out of this view and take a look at graphing each piece. In other words, I'm still not seeing where we've gone wrong. It still looks like pi checks and it should work, right? So the question is, why are we not seeing it on difference? Let's do this. I'm going to focus on the left-hand side of that equation and we're going to zoom out. So this is kind of an interesting looking graph. And part of the reason I want to do this is maybe it's catching something and be able to go back and look what's happening. So if you graph 18, Desmos doesn't know what to do, it's just 18 here. When you have just this part, it's assuming this is a y equals because you're giving it an x. That's what I was trying to explain earlier. Not sure if it quite made sense. But here, putting y equals tells us this part, whereas putting the y equals in the one, the first one doesn't do anything. So look at this guy now. And this is a little bit tricky because when we look back at this, now the intersection, I see pi/3, I see pi, and I see pi/3. Those are my three solutions. And when we go back, I'm just going to type the whole thing here again so we don't get rid of that. Ooh, this is interesting. This equation, oh, they didn't tell us this earlier. Oh, 19, not 18. We're going to come back to that. I've never seen that error message. I'll learn with you live what's going on there. Let's go back and type 18. Oh, yay, it still has it. Okay, I kind of like this because when I put that in at first, it didn't give me this equation contains fine detail that has not been fully resolved. We'll learn more together. But when I take a look at this, notice it's missing that intersection right here, right? It's getting those two. So this is one place where Desmos fails a little bit, and you guys want to be cautious of like, don't just look at your solution and say, I'm wrong. Think about all the different ways that Desmos is representing this, and it's helpful to think about the two pieces because we can see it. If I take it off there, that between 0 and 2 pi, I have 1, 2, 3, whereas you can't in this guy. It's missing that middle one. Okay, let's learn more. I want to learn more. Oh, fascinating. Desmos says, I'm not as smart as you guys, basically. Sometimes the calculator checks an equation is too complicated to plot perfectly in a reasonable amount of time. Plot at a slower resolution, which means it's kind of like missing a little bit. Oh, fascinating. And it's missing a solution. So here's my recommendation. When I'm teaching you these two Desmos ways, do both, right? So you're both going to do this. Ooh, what a fun problem. Let's take a look at another one. I'm sure you guys are thinking, man, that one's not so fun. I don't want that to happen to me. But with practice, you'll make sure you know when it's happening to you, because you'll be able to spot it. So I want to give you one more that is a variation. We're going to start this one, but not work all the way through it. Because once you know the trick, it's very similar. Click to share here. So the one we're going to look at is 2 sine squared equals 2 plus cosine x. Hold on just a second, guys. That'll work. Sorry, guys. My little one was watching the video, and I don't know how much it'll pick up in the recording. I think you guys can hear me okay. But you guys might have been hearing all about Legos. Okay, so let's return to this. Distracted here. But this one, the main feature you're probably noticing different is this one has a sine squared, and a cosine. So in this particular case, we have a problem. Even though it looks like we're going to have a similar situation with a quadratic to the other one, we have to go ahead and transform to all one trig function if we can. Now, it's not always possible, and there's some other techniques to just look at the graph and graphically find the solutions if we can't figure out how to do it by hand and convert it to a quadratic equation. But in this case, here's the trick. Anytime you see a sine squared, we know that there's a connection between sine squared and cosine squared. That sine squared plus cosine squared equals 1. So if I want to replace sine squared, I always know it's true, because this is an identity, that sine squared equals 1 minus cosine squared x. So if you're solving this by hand, this allows you to plug in. And now everything has cosine. Let's take it one step further, and then we'll go on and look at a variation. So I think once you see this, it's very similar to the other. So if I distribute my 2, it's kind of nice in this one. Notice we've got some symmetry as 2's canceling out. But then I could go ahead and add my 2 cosine squared to the other side. And continue from here. Okay, so at this point, I would want to factor out my cosine, then set each factor to 0 and solve. So I'm going to leave that to continue for us, or to continue for you on your own, because I feel confident you can handle this. Before we continue, any questions on this one or anything that we want to return back to? Okay, so I'm not seeing anything pop in the chat. So let me show you one more really quickly, and then I'm going to show you your Desmos activities and let you get started on this. So for this one, our last equation together right now is tangent, and I'm going to write it like what is I wrote it actually. Tangent of 3x minus 1 equals 0. When you're reading this on a letter sign, they kind of wrote it like this, where the 3x is close to the tangent. And when you see this, you want to assume that it's really meaning tangent of 3x minus 1. If they had wanted it to be 3x minus 1 in parentheses, they really need to specify that. It's kind of understood. The argument is immediately what's following, not including any plus or minus, unless you put those parentheses.
Just right.
Now you have to hear the Legos.
Place a 2.4.
Sorry, he thought his headphones were plugged in. So let's take a look at this one. It's okay, Harrison. They understand. You want to come give everybody no. First grader. So let's take a look at finishing this one. Isn't that video bombing today? So if we go ahead and add that one, we're looking for all the places where the tangent is 1. Now, what about this 3x? Well, I want you to just forget about it for a second. Forget that it is that, right? We're saying, where is the tangent 1? And then if we can figure out where the tangent is 1, we can set 3x equal to those angles and solve for our x. So we're going to have to do a little bit of work after we go backwards to our trig functions. Now, think about unit circle. How many times have I said unit circle today? But unit circle, we know the tangent is 1 when our sine and cosine are equal. Sine and cosine are going to be equal at 45 degrees. Then they're also going to be equal at, let's see, 5 pi over 4. So adding the pi over 4 for 225 degrees here, those two places. So think about, in this case, think about it as if this were just an x, we would have found two solutions. The angle would be pi over 4, but it's not just the angle. It's actually a 3x. So at this point, you're sort of doing the same process, saying, what is the angle? What is that missing part? What is the theta? As if theta is 3x. And then you can divide by 3. And we divide by 3, same thing as multiplying by 1/3, pi over 12. And then 5 pi over 12. So notice what happens is we're seeing the angle where the tangent is 1 pop out here. And then this rotational speed, we're rotating 3 times faster. So we get to it faster, if that makes sense, 3 times as fast. So sometimes it's hard to understand why these are going the way they're going. The Desmos activity talks a little bit more about this rotational speed, but from a solving it perspective, you're just waiting to divide by 3 until the very last step, because you have to get rid of the tangent part before you can get up. So let's go ahead and I'm going to see if there's any questions, and then we'll pop over to your Desmos activities. The questions here. One more quick note on this one. We probably need to check it on Desmos and make sure it works between 0 and pi over 2. In particular on this one, there are the things that I would be worried about. This one, we have to be a little bit careful with our specific solutions and our general solutions, because normally we would take each of our specific solutions and just add 2 pi. But what was really happening, if we think about this, before we switch over to Desmos, what's really happening is it's kind of like the tangent was 1 if you're pi over 4 or any 2 pi multiple at that stage. It's like before you divide by 3 in this case. So you'll see why I'm going to change this modification, but we may need to change that. In other words, the plus 2 pi worked when our rotational speed was just 1. We were doing 1 revolution per minute. If we're doing more, we maybe need to reconsider that. So hold that thought. In other words, this 2 pi kind of was attached to those two. So let's jot this into Desmos, check the 2 specific solutions we have, and then see why maybe those are not the only 2. So let's see. Stop the share. Sorry guys, technology problems here. And let me share Desmos. Oh yes, we had unresolved plotting issues. That's where we were. So on this guy, let's go ahead and get rid of this. I love that we kind of broke Decimus a little bit. What fun. But go ahead and graph tangent f3x. Kind of fun. Oh my, that looks a little crazy, right? And then y equals 0. Let's definitely take this between 0 to 2 pi. And oops, not very tight. 2 pi. And then for our steps, these have multiples of pi over 12, so I'm going to change my step. Whoa. Why did not do it? Why did you not do it? Why did you not do that? Oh, 0. Okay, so now we're on the right track. 0 to 2 pi. But what I'm looking for here again is the intersections, because I have it in 2 pieces, or if I just add 1, I usually get that first. I have more than 2 between 0 and 2 pi. So look at these first 2. This first 2, that's pi over 12. That was our first one. And then 5 pi over 12, our second one. So what is happening is normally we would add plus 2 pi n to each. But when we divide by 3 at that very last step, we need to also go ahead. Oh, look, we got that same detail, but it looks like it actually is displaying it. Interesting, I have to investigate. But when we're dividing by that 3, we really need to divide the 2 pi by 3. In other words, here, we're not cycling in 2 pi's. We're cycling in 2 pi over 3 in this case. So let's go back and see if adding that 2 pi over 3 fixes things compared to the solution. And if it doesn't, we'll rethink our thoughts. In other words, it seems to make sense that if we're dividing that pi over 4 by 3, then we should divide how we're cycling this. Excuse me. So let me share this. So I want you guys to understand why you're not just doing a plus 2 pi in. And sometimes when we're working through these, we just forget and put it there. And then when you see the graph, hopefully it'll trigger your brain to say, oh yeah, I did something a little different. So in this case, what I'm proposing to us is that we take this pi over 12, and instead of plus 2 pi n, we do that 2 pi n, and we divide by the 3 that we saw before. So let's say that my n equals 1. In other words, instead of adding 2 pi, I'm adding 2 pi over 3. See where that puts me, and then we'll look back at our Decimus graph. So pi over 12 plus 2 pi over 3. Fraction time. If I do that right, I get 8 pi over 12 instead of 2 pi over 3. And then when I add 1 pi to it, I get 9 pi over 12. And then if I reduce that, let's see, I get 3 pi over 4. Interesting. Right? So what I'm proposing to you is when I look back at Decimus, we should see 3 pi over 4 as also a solution. Yeah, let's look. If it's not, we need to rethink this rotation idea and make sure we're not doing it in the wrong way. We also need to be a little bit careful because we have this issue on this other one. But let's see. So 3 pi over 4. Okay, so first solution, second solution. This is the first solution moved out by rotation, but one rotation in this case we have to adjust because of the rotational speed of 3. So instead of adding 2 pi, we added 2 pi over 3, and our next one is 3 pi over 4. Now, if we took 5 pi over 12 and added 2 pi over 3. That's going to get us here. Now, or should get us there. Let's see. And then we have another and another, right? So it's really taking those two solutions and continuing to move them. So just to kind of reiterate what we're doing here. This will help us visualize it a little. Pi over 12, you see that guy? Plus 2 pi over 3. Ooh, that guy. And then if we add, that's n equals 1 rotation. If we add 2 rotations, there's that guy. So what happens is that one solution between 0 and 2 pi for the pi over 4, when we divide by 3, ends up being 3 solutions between 0 to 2 pi on this guy. So fascinating. Now, in this particular case, I'm going to show you a trick. But the other one, we had, what was it? Back here, 5 pi over 12. So when we do 5 pi over 12, if we do 0 to pi over 3, that's the first of the second solution. And then if we do times 1, it's the next rotation. And then 2, it is at the end over here. Oh, we're down less than a minute. It may boot us off Zoom. If it boots us off Zoom, just rejoin because I do want to show you the Desmos. But this is kind of cool. So I want to squeeze in writing out these solutions if I can do it. Because what we want to do is we really want to say these solutions are pi over 12 plus 2 pi over 3 n, or 2 pi n over 3, and 5 pi over 12 plus 2 pi n over 3. Okay, it may cut us off here in a second. Again, it's telling me that it's going to cut us off. Sometimes it doesn't though. We'll take our chances. So that is a little bit more complicated. Let's go ahead and I'm going to take us over to our Desmos. Just so I know that you guys are still here, drop a yes if you're still hearing me. Make sure it didn't like cut you guys off and I'm talking to nobody. Ooh, I see my chat box. Okay. Thanks, guys. Yay. Okay, good. So what I want to do, so I need to figure out why Zoom boots me sometimes and doesn't boot me others. Working on it. So what I'm going to show you is 2 Desmos activities. And these Desmos activities are going to walk you through exactly how I've been showing you how to do it. But once you've done it by hand and on Desmos, it'll make these easier. This code is not on Blackboard yet, but if you want to go ahead and put it in, get into it. I'll link it later so that if you're watching this recorded, that the links will already be into Desmos with the videos.